Okay, today's lecture is about Amdahl's law, speed up and parallel computing. But before going to this, I will talk about briefly about the why not to use parallel distributed computing and why we use parallel distributed computing. Okay, first, in which situation we will use, and first we'll consider why we use parallel computing. The first one is solving larger and or more complex problems. And second one, provide the concurrency. It means solving the problem at once. Third one is take advantage of non-local resources. If the non-local resources are there, then we can use the PDC, parallel distributed computing. Fourth one, make better use of underlying parallel hardware. We can say like we have hardware. In each there is the process is parallel and there is multiprocessor and the multi-core system is available. Then we can use the PDC, parallel distributed computing. Then it is mandatory. But if our process is not complex, or we can say our problem is not complex, then no need of using parallel distributed computing. If you use, then it will be wastage. For example, there is a 5 kilowatt generator, but we're using one light and one fan, then it is no need of using the 5 kilowatt generator. So another example we can say like there is a small family like 3 to 4 members. They have a van, but it is like 15 to 15 seats. The father brought, we can say like that. Then it is wastage for 3 to 4 members. The 15 seat van is bringing 15 seat van. Then there is we can say that PDC is not no needed for this. If there is no complex, then no need of PDC. Then even no concurrency, no local resource, no, then no need. So if the hardware is also not parallel, then the PDC is no need of that. So parallel means we can say we do have more processors, and at the same time it will work parallelly. Distributed means it is not like that. It is in different places. Those are autonomous and they are connected through a network. Okay. So why we use distributed computing? Like we can say historically, like work together from different places connected via network. And the functional, we can say the next one is functional. Why we use distributed computing? First of all, we can say historical, and then functional, and then economical. If we go to the historical, like I said, it will work together from different places, connect via a network, one network. We can say like combining all the work, then we need distributed computing. Second one is like functional. It is like resource sharing, like software and hardware. If there is a software or hardware and it is high cost, then bringing one and sharing with others through the same network, should be through the same network. And if we jump into the economical, it is separate collaborative working units. Like we can say, rather than purchasing a computer with high power, we can purchase multiple computers with less power and connect each other through the same network. This way it will mostly like cost and maintenance is low. So also if there is any problem, then we can replace with it only, no need to change the entire unit. So like that it will go. So now we will start with the Amdahl's law, speed up and parallel computing. Okay, and mainly this presentation explores the fundamentals principle of Amdahl's law, a key concept in understanding the performance limitation of parallel computing. We will dive into the formula and its implications and real world applications. Okay, so how we'll start? Like first we will jump into the introduction. Like we can say Amdahl's law predicts the theoretical speed up of a task when a portion of it's parallelized. It helps evaluate the performance limits of parallel computing. And why it is important? Like we can say it's identify the bottlenecks. It means It highlights the sequential parts of a program that limit performance, guiding developers to focus on optimizing those areas. And the second one we can say like practical optimization. Okay, so it helps the determine whether adding more processors or resources will significantly improve performance, preventing over investment in hardware. Mainly we can say like adding more processors or resources will significantly improve the performance. Third one we can jump into like performance predictions. And the fourth one, foundation for scalability analysis. And the fifth one, guidance for the application design. Uh, and then we'll jump to the formula. The formula is like the speed up is equal to 1 by 1 minus p plus p by s. Speed up, we can say the factor by which is the execution time is reduced, and the p parallelizable portion, and the 1 minus p sequential portion, and the n is number of portion. The basic, what is the basic? Which gives the Amdahl law, which gives the theoretical speedup in latency of the execution of a task at fixed workload that can be expected of a system whose resources are improved. Okay, that means the scalability. So we can go now into the formula as I said. So like speed up is like with the number of processors, and the p means parallel fractions, and the sequential fraction is 1 minus p. So if you go to the example, we can see like here, suppose that 80% of your program can be parallelized and the 4 machines are used to run your parallel version of the program. The speed up you can get according to Amdahl's law is like, we will now put the we will put the values for the equation, then we will get for 2.5 times it is. Although you use 4 processor, you cannot get a speed up more than 2.5 times. Also, we will go for the like key concept parallelism versus sequential work. Sequential, this portion cannot be parallelized and limits overall speed up regardless of the number of processors. Second thing, parallelizable. This portion scales linearly with the number of processors, but its impact is limited by the sequential portion. Third one is we will got limitation. Speed up diminishes as number n increases. Okay. Then we will go for another example. If there is 60% of program parallelizable and number of processes n we call as, so p is equal to 0.6 we will assign, and y minus p we will put the 0.4. And as I said, 60% is parallelized by program with 4 processes. P is equal 0.4 and n is equal 4. If we drop the values for the equation, then it will come like this, and s will be 1.82, but which means program runs 1.82 times faster with 4 processors. And second example, if there is 90% with 8 processors, then p means 0.9 and n means 8. Now we will put the values for the equation, it will get 4.71. Okay, then I have summarized the calculation like this easily, you can see. And the next one is like visualization, speed up versus the processors. For example, I have shown this graph illustrates the relationship between speed up and the number of processors for different values of the parallelizable portion. As the number of processors increases, speed up initially rises rapidly, but eventually places due to the sequential portion of the task. And then we will see the practical example, like we can say it is used for the video rendering, and you can see video rendering is the main part, and parallel as well. Frame processing can be done in parallelly, significantly reducing the rendering time. Sequential you can say loading metadata for the video like times and the audio tracks and remain sequential. So if you go to the limitations of Amdahl like even with the infinite, it will go. Maximum speed up is 1 by then 1 by 1 minus p. Example, if we can say if the p is equal 0.9, 90%, that means then max speed up will be 10x. Okay. Then sequential bottlenecks. It means the sequential portion limits the maximum achievable speedup even with an infinite number of processes. Okay. Then also fix the problem size. That means Amdahl's law assumes a fixed workload which may not reflect real world scenarios where workloads can scale. Okay. Also overheads, we can say overheads limitation. No, this is enough. This thing even with infinite and the sequential bottlenecks and the fixed problem size. Then we will go to the Gustafson's law counterpoint. This means highlight scalability by increasing the problem size. What do you mean by the scalability? Scalability means it is the property of the system to handle a growing growing around like work by adding resources to the system. Then the contrast with Amdahl's law, which assumes the fixed workloads, and the key insight is like we can say larger workloads increases and the enhancing parallelism. And before this, I'll again say why we use the Amdahl's law has practical constraints like sequential bottlenecks, even the infinite processors, sequential parts we can use like for in the maths 1 minus p and the overheads like synchronization, communication and the load balancing reduce practical speed up and the Gustafson's law we will use and we will go for if we ask a real world application in Amdahl's law it's we can say matrix multiplication, rendering in graphics and machine learning and why it's important I'm again saying recapping identifies the bottlenecks, practical optimizations, performance prediction, foundation for scalability analysis, guidance for application design. So this is the I have again recap and conclusion. Amdahl's law explains speed up limits in parallel computing, shows the trade-off between sequential bottlenecks and processor scalability. So implication for system design, balance between hardware and software parallelism. So that's it for today. Thank you.